Hey everybody, Dr. White here. I'm going to talk about some random variables that are associated with normal distributions. We'll be making heavy use of a lot of the theory that we've done in recent sections. And the moment generating function technique is going to be a big star today. So let's get started. Suppose that x1 through xn are independent, and each one of them is normally distributed, but with its own mean mu I and its own variance sigma I squared. And let's let y be a linear combination of the xi's, so sum of constant ci times xi. For some reason in this section, the textbook calls the constant ci instead of ai, whatever. Okay, we already know that the mean of a linear combination is linear combination of the means. And the variance linear combination is the sum of the squares of the constants times the variances of the individual xi's. But because the xi's are normal, we're working with this extra assumption here, it turns out that the linear combination is normal with that mean and that variance. So let's get a proof of that. The moment generating function technique will be our friend. Let's look for the moment generating function for capital Y. Well, capital Y is a sum. It is a sum of CIXI's, okay? Now the XI's are independent of each other. Therefore, the CIXI's are independent of each other. You know, like if I have a 2x1 and a 5x2. If I told you the value of 2x1, you would know x1. But that wouldn't help you know x2 because they're independent. So you wouldn't know anything more about 5x2 than you knew before. So the CIXI's are independent because of the independence of the xi's. Okay, so I'm looking at a sum of independence. Therefore, its moment generating function is the product of the moment generating function of those things that are summed up. But what's the moment generating function for CIXI? It is the expected value of e to the TCI. You know, what it is at t is equal to e to the t CIXI, right? By definition of moment generating function for CIXI. Okay, and I stare at this little product and I just regroup a tiny bit like that. Commutativity, multiplication, associativity. And I'm looking exactly at the definition for the moment generating function of xi, but applied to CIT. Okay. Now, I know the moment generating function for xi because xi is normal. I go to my head, and the moment generating function for normal mu sigma squares is e to the mu t plus sigma squared t squared over 2. That's all in the power of e. So I just jot down the moment generating function for the xi at CIT. Okay, so I stick in a CIT wherever there was a t over in this formula. I put in a CIT, and I got to put in a mu I, and I got to put in a sigma I instead of a mu and a sigma, and I get this stuff. Okay. The CI squared t squared is when I square out the CIT. Now, that's a product of exponentials, so that can become an exponent for a sum. And when I do that, and I gather things together, I got e to this stuff times t plus this stuff times t squared over 2. So that totally fits the form for the moment generating function for a normal. And so now I know that y is normal. Yay. Okay. Important special case of this little result. Suppose that y is equal to x1 minus x2, where each of them is normal with their own mean and variance. And let's say they're independent of each other. So it's the difference of two independent normals. Then our result tells us that y is going to be normal Now, its mean is going to be the linear combination of the means. So, thinking about this, this is a linear combination. 1 times x1 plus -1 times x2. And so linear combination of those means. 1 mu1 plus -1 mu2. So mu1 minus mu2. And then the variance is the sum of the ci squared's variances. C1 squared, first variance, C2 squared, second variance. So that just works out to sigma1 squared plus sigma2 squared. So y is also normal. The difference in normals is normals. And interestingly, the variance of the difference is the sum of the variances, not the difference of the variances, sum of the variances. So here's a way that's useful. Suppose you got a population of Georgetown College males, some big population, and if you made a histogram of them, what if it looked like completely bell-shaped, centered around 72, say with a variance of 3 squared, 9, so the standard deviation is 3, okay? And so your typical Georgetown College male is 72 inches high, give or take 3 inches or so. So say I pick a Georgetown College male at random, then that would give me a random variable, and its distribution would be normal, mean 72, variance 9. Now, same for females. Let's say their population is normally distributed with a mean of 68 and a standard deviation of 4 for a variance of 16. Typical female, 68 inches tall, plus or minus 4 inches. Okay, and if you grab a female at random, then her height would be a random variable that's normally distributed, mean 68, variance 16. Suppose you pick a male and a female at random and independently of each other. What's the chance that the female is taller? All right, let's set this up. So let's let x be the height of the random male and y be the height of the random female. So they've got those normal distributions that you see up here. Let's let d be the difference, x minus y. Then our result says that d is normal with mean, 72 minus 68 is 4 inches, and variance, sum of the variances of those two normal random variables, that works out to 25, okay? So it's normal, mean 4, variance 25. And we're looking for the chance the female is taller, so we're looking for the chance that the difference is less than 0. In your mind's eye, you imagine a bell-shaped curve centered at 4, and you're wondering what's the shaded area underneath it before 0. Okay? So you could head to P norm, 0, mean is 4, and you got to switch to R's way of thinking where it sticks in the standard deviation. So you got to put in a 5 there. Very easy to miss. And you get about 0.21. Okay. Here's another kind of useful consequence of this result about linear combinations. X bar, the sample mean based on a random sample of size n. That's a linear combination of the x1 through the xn. It's just each one of them multiplied by a 1 over n and added together. Now, we know that the expected value of x bar is mu, and we know the variance of x bar is the variance of whatever common distribution the xi's are from divided by n. We know that. But what if we make an extra assumption about the common distribution? What if their common distribution for those xi's is normal? Okay. Well, then this linear combination result would tell us that the x bar is normal with that mean and variance. So the part that's new for us over what we already know about x bar is the normality. Okay, and that's coming off this moment generating function technique. It's so wonderful. Okay, so as a little example of the implications of this, say that you would like to estimate the mean height of all Georgetown College females, but you only have time to pick one female out of the population, and you'll just use her height as a guess for the mean of the population. Okay. Now, unknown to you, the mean is 68. Okay. What's your chances of coming within 2 inches of the correct mean? Okay. So you're asking for the chances that the female you pick is between 66 and 70 inches tall. So we think here. The underlying distribution, population, is normally distributed, mean 68, and variance 16, 4 squared. You're looking for this shaded area here. And so, you head to P norm 70, 68, and then you got to do the square root of the 4 squared, which is 4, put in the standard deviation. Look how easy that is to miss. And then you got to subtract off the chance of being less than or equal to 66. And so, like, once I corrected my own error, sticking in the variance instead of the standard deviations, I get 0.68. Now, so that's, pretty decent chance to come in within, that seems wrong. Why is that wrong? 70, 66. That is just wrong. That is not 0.68. It has got to be something else, because I know that in a normal curve, there's about a 68% chance of coming in with 1 standard deviation of the mean. Now here, 1 standard deviation is 4. Okay, so there'd be a 68% chance of coming within 4 of 68. So that's from 64 to 72. So this chance here better not be 68%. It better be something smaller. So let me go and do these computations again, because I think when I corrected some typos, I did it wrong. Let's just head to R and let's get the right answer. So I happen to have R up somewhere. Here it is. And so I need to do P norm of 70, where the mean is 68 and the standard deviation is 4, minus P norm of 66, where the mean is 68 and standard deviation is 4. Okay, 0.38. That's much better. Okay, so that should be about a 0.38. So I'm going to go ahead and make that correction over here in my notes. So when you get your copy of this PDF, it'll show the correct thing. Okay. Now, so you get this kind of like miserably small chance of coming within 2 inches of the correct mean when you just estimate based off of one randomly grabbed person. But what if you grab more people? What if you took a random sample of 25 Georgetown College females and computed their sample mean? What would be the probability that the X bar, the sample mean, would be between 66 and 70? What's your chances now of coming within 2 inches of the right answer? Well, by our theory, X bar is normal with mean 68 and variance 16 over 25. So the standard deviation of that would be the square root of that, which would be a 4 over 5, which is a 0.8. And so we could get our probability by doing that in R, P norm 70 minus P norm 66, but now throw in that the standard deviation is 0.8. And you get a much larger chance of coming within 2 inches of the correct answer. So intuitively, this should make sense, right? Because when you grab one person, they could be 68, give or take 4 inches or so easily. When you grab 25 people, each of them could be easily 68, give or take 4 inches or so. So you get some tall women, you'll get some short ones, but the talls and the shorts will kind of cancel each other out when you're taking that sample mean. They'll cancel out around the sample mean. And so the sample mean is probably going to be, a lot closer to the mean of the population than any one individual is likely to be. So that's the intuitive, that's the practical result of the variance of the random variable going down from sigma squared to sigma squared over n. Okay, shift gears a little bit. Suppose you got a random sample of size n from a normal distribution x that has a mean mu and variance sigma squared. And let's say that you don't know the mean of the random variable and you don't know the variance of the random variable, but you would like to estimate the variance, okay? So what is the variance by definition? It is the expected value of x minus mu squared. So one possible strategy might be this. You don't know the mean, you don't know the variance, but you've got these tries of the random variable, x1 through xn, and you could compute their sample mean x bar. So you could compute the deviations of each of them from their sample mean and square, okay? And if you average them up, wouldn't that be some approximation to the expected value? Because the expected value is like what you get in the long run if you try the random variable again and again. Well, we tried it n times, so maybe the average of what we got should be near the expected value. That's a pretty good idea. It's a pretty good idea. But it's a bit of an underestimate. That's a typo there. I'm going to correct that. It's actually a bit of an underestimate of sigma squared on average. I mean, sometimes it could turn out bigger than sigma squared. Sometimes it could turn out less than sigma squared. I mean, this is a random variable after all. But the expected value of that is actually a little bit less than sigma squared. And the reason for that is because that in there is not a mu. You don't know mu. You can't use it to compute these squared deviations. And so you're just like guesstimating it with x bar. But you see, the thing is that x bar is tailor-made to try to be close to all the xi's at once. It's the single best number that's close to all the x bars at once. And so it's probably going to be like a little closer to all the x bars at once than mu is. And so these numbers here, this sum here is probably going to be smaller. In fact, it is almost certainly going to be smaller than what you would get by sticking in a mu here. In fact, it could be proved mathematically. It works just like the first version of the bizarre sorcerer problem. It could be proved mathematically that of all the numbers that you could stick in there to try to make this small when you've got some x1 through xn already in hand, the mean of the x1 through the xn is the one that makes that smallest. It would be smaller than the mu, unless it just happened to be exactly equal to the mu. So this is going to be a bit of an underestimate on average. Actually, to correct it, to get the expected value to be exactly sigma squared, you need to divide by 1 less than the sample size. That actually works. No matter what your underlying random variable capital X is, that expected value is going to be sigma squared, okay? As long as the underlying random variable does have a variance, sigma squared. It'll work. I'm not going to prove that today. It's not too terribly hard to prove. We might do it sometime when we're together. Instead, I'm going to go ahead and look at what how the book treats this, they're going to make the extra assumption that x is normal, okay, which is, we're doing up here, and they'll learn a little bit more about this estimator quantity with that extra assumption. So here's the book's theorem. It says, if the underlying distribution x is normal, and you're taking this random sample x1 through xn from it, so you compute the sample mean x bar, and if you compute that estimator, the one here, and we're going to call that capital S squared, because I'm thinking of it as an estimator of sigma squared, so it kind of makes sense to call it something similar. If you compute those two, it turns out that as random variables, they're independent. That is independent of, that, which seems really wrong and false, you know, because this has an x bar in its formula. You know? How can it be independent of this? It was a big surprise to statisticians when they discovered this. It was like, whoa! And then when they, of course, the deeper they look into it, the more they realize this has to be true. It's amazing. But anyway, they're independent. And furthermore, if you just tweak the s squared a little bit, if you get that n-1 off the bottom by multiplying by n-1, and if you divide by the variance sigma squared, that random variable there turns out to be chi-square with n-1 degrees of freedom. Okay, so that's the book's theorem. You might wonder, well, what does that have to do with s squared being an unbiased estimator of sigma squared? What does it have to do with the expected value of that being sigma squared? Before we go into trying to look deeper into the theorem or prove parts of it, let's at least see how it relates to that question. Well, first of all, notice we know the mean of a chi-square random variable. It's equal to its degrees of freedom. So if the theorem says that doohickey is a chi-square, then its expected value is going to be n-1. And there's a 1 over sigma squared in that expression, which is a constant, so I can factor it out of the expected value because expected values are linear operators. I can multiply both sides of that equation by sigma squared and divide both sides by n-1, and I can get this. And then the 1 over n-1 is a constant, so I can work it inside the expected value, and I've got that the expected value of s squared is indeed sigma squared. So off of the chi-squaredness, this comes immediately. So let's prove the theorem. Well, we're not going to prove all of it. We're not going to prove the independence part, the part that those two are independent. That is actually very tough to prove. If you go to grad school of statistics, you'll prove it. But we'll use the independence to prove the second part, that this doohickey here, the sum of the squares of the deviations over the variance of the random variable, is chi-squared n-1. So we're going to prove that. And I'll tell you right up front what our strategy is. We're going to use the moment generating function technique. We're going to come up with the moment generating function for this doohickey, okay? And it will find that it's the moment generating function for a chi-square with n-1 degrees of freedom. That'll clinch it. So let's go. Well, not quite yet. We need a couple of little warm-up observations. First little warm-up observation is, what happens if you were to sum up just the deviations from the sample mean without squaring them, okay? Sum xi minus x bar. Well, you could do that by summing the xi's minus the sum of the x bars. That's just n of them. Now, by definition, x bar is the sum of the xi's over n. So once you cancel out those n's, here, then you got the sum of the x bars minus the sum of the x bars. That's 0. So the sum of the deviations of a sample around their sample mean is always 0. Nice to know. Next of all, remember that fact we proved a few sections back about normal random variables. If you subtract off their mean and divide by their standard deviation, you get a normal 0, 1 random variable. Random variable with mean 0, standard deviation 1, that's normal. Standard normal random variable, we called it. So if I just let yi be xi minus mu over sigma, it's a standard normal. Another thing is that the yi's are all independent, and that's because they're each built on different xi's, and the xi's are independent. Okay. Well, now I'm kind of ready to go into the proof proper. To do it, I'm going to construct a random variable that looks a lot like the one that I want to show as chi-square n minus 1. The one that I want to show as chi-square n minus 1 is this guy where you're doing the deviations from the sample mean. Okay? I'm going to look at the sum of the squares of the deviations from the mean and divide by a sigma squared, so I could just work that inside the square. So this is very similar looking to my mystery random variable, but not quite. It's got a mu instead of an x bar. And because of that, everything changes. That's a standard normal. It's a yi. We're looking at a yi squared. We're looking at the sum of the squares of n independent normals. Do you remember that the square of a standard normal is chi-square with 1 degree of freedom? So we're looking at the sum of n independent chi-squares with 1 degrees of freedom. We used the moment generating technique in the previous section to show that that would be chi-square with degrees of freedom equal to the sum of the degrees of freedom of all the chi-squares you're adding up. And 1 plus 1 plus 1 plus 1, n times is n. So this w is chi-square with n degrees of freedom, which should be promising. You know, when we want to show that our random variable, our mystery random variable, is chi-square n minus 1, and this w here, which is so similar to it, is chi-square n, that should give us some hope. What we should do then is see if we can relate the w to our mystery random variable. So the mystery random variable was the same as w, except it had like an x bar instead of a mu right there. So when I start with w, I'm going to see if I can work in an x bar. So I've got sum I goes from 1 to n, but on the top of that fraction, I just do a minus x bar plus an x bar. So I'm not changing the quantity at all. And so now I've got this fraction that I got to square out. And of course, I could just square out the top and square out the bottom, and I got to add them all together. So what would happen when I do that? Well, I get a lot of stuff. Because when you square something out, it's the first term squared plus twice the product of the two times the second term squared. And so I'd be summing up my first term squared. I'd be summing up my middle terms. And I'd be summing up my last term squared. But those are the same no matter what the I is. So I actually just have n x bar minus mu squares right there. And I've got the sigma squared on the bottom, and so I'm breaking up the fraction into those three, so each needs a sigma squared on the bottom. Okay, now that first one is my mystery random variable. That's the one that I want to show as chi-square n minus 1. I can rewrite that slightly the way they did when they stated the theorem, n minus 1 s squared over sigma squared. So I'm just rewriting it like that. But what else is present? I've got this awful middle term. Gee, I hope it goes away. I've got that final term. That looks a little simpler. Let me think about it first. I'm procrastinating here. Leave the hard stuff for later. Well, you know, I could actually rework this x bar minus mu squared over sigma squared times an n up here. Instead of times an n, I could say sigma squared divided by n. If I divide the bottom by n, that's the same as multiplying on the top by n. And then I could actually express the whole thing as a square, like that. So get some pencil and paper. I'm sure you already have been working through with pencil and paper as you follow along. Use your pencil and paper and see when you square this out, can you bring it to this? It works. Now, why do it? Well, remember x bar is normal with mean mu and variance sigma squared over n. So I'm taking x bar and I'm subtracting off its mean and I'm dividing by standard deviation. I am creating a standard normal and I am squaring it. So my result, this stuff here, is the square of a standard normal. Wow. Okay, now what about this hard stuff? Well, the 2 and the x bar minus mu don't change as the I changes in the summation, so they can factor out. What you're left with is the sum of the deviations of the xi's around the x bar, which is 0. Whoa, so that goes away. So what we've got is this w, which we know is chi-square n, is equal to the sum, our mystery random variable plus the square of a standard normal. And you know, the first part of the theorem, the part we're not proving, said that s squared and x bar are independent. And this guy is built off of s squared. And this whole thing is built off of x bar. So this and this have to be independent. So my w is a sum of 2 independent random variables. So its moment generating function is one that I'm going to be able to find pretty easily. So let's think about the moment generating function of w that way. So here's w, the sum of those 2 independent random variables, and I want its moment generating function at any t. Well, by the independence, that's got to be the moment generating function of our mystery random variable at t times the moment generating function of a standard normal squared at t. A standard normal squared is chi-squared with 1 degree of freedom. I can write down its moment generating function right there. But another way of writing down the moment generating function for our sum is to remember that that sum is w, which is chi-squared with n degrees of freedom. And so the moment generating function is that. So we get an equation. That is the moment generating function of the random variable that we want to show as chi-squared n minus 1 times that. Solve for this. You will get this. And when you look at that, that is exactly the form for a chi-square random variable with n minus 1 degrees of freedom. Moment generating function technique strikes again. Phenomenal. So just thinking a little bit, because of that fact, because of the fact that s squared is an unbiased estimate of the variance of the distribution that you're randomly picking from, it's set up in most statistics computing systems for you to be able to compute it quickly off of data. So like say you have picked from some distribution n times, you've done n tries, and they're x1 through xn, and you want to get the sample variance of them. there's a function called VAR in R that'll get it for you. It'll compute this quantity for you. So let's just give it a little bit of a try. Like say my data is the numbers 1 through 5. And if I were to compute the sum of the data minus the mean of the data squared, and divide that by how many data points there are. Okay, well, data there is the numbers from 1 to 5, 1, 2, 3, 4, 5. So that's 1 less than 5. Whoa. Data minus, oh, I got my square, I got my parentheses in the wrong place. There we go. 2.5. And if I tried variance of my data, 2.5. Yeah, so that's what var is doing. By the way, the square root of the sample variance would be called the sample standard deviation. So the square root of 2.5, 1.58, and there's actually a function in R called SD, I think. Yes, it is. And if you do the SD of the data, you get the same thing. It's just taking the square root of variance for you. Now, just a little question for you. The expected value of S squared is sigma squared. Do you think that the expected value of S, the square root of the sample variance, would be equal to sigma? Just a question to think about. There's one last really big theorem in this section. It's called student's t-distribution. The reason for this is that it was first kind of worked on by a guy named William Gossett, who worked at the Guinness Brewing Company in the United Kingdom, late 1800s, and he developed this statistic. He developed the random variable that's talked about here as part of basically doing some statistics around quality control in brewing. And he wanted to publish his results, but his employers, they wanted to kind of not let competitor brewers know that this great stuff had been developed by them. So they asked him to use a pseudonym, and he chose the name Student. So this is called student's t-distribution. Take a random variable capital T, and it works like this. You've got a standard normal random variable Z. You've got a chi-square random variable with r degrees of freedom, call it U, and it's independent of Z. And you just create this crazy looking fraction, Z over the square root of U divided by its degrees of freedom. So that whole fraction U over R here is inside the square root sign. If you got your random variable defined in such a way, it's considered to be a member of the T family, little t there, of distributions. It's said to be T with R degrees of freedom. And the interesting thing is that you can determine the distribution of this random variable. The PDF here is kind of god-awful with a lot of gammas, computations, and there's a pi thrown in there, all kinds of stuff. But it can be found, so you can get probabilities for this random variable. And so the theorem is that the PDF is this. In no way, nobody ever remembers this. They just let the computer figure probabilities. Believe it or not, there is a T there is a T family of functions, PT, DT, RT, in R. Sorry. So we're not going to prove that theorem here, but you should totally study the proof because it's a wonderful example of clever use of the CDF technique, actually. You basically try to get the CDF for capital T, and then you take the derivative of the CDF and you end up with the PDF. I want to just gesture at why these T distributions are so important. Say that you've got a random sample of size n from some normal distribution, where like maybe you don't know the mean and you don't know the variance, okay? But maybe you're hoping that your sample mean could be a good estimate of the mean of the population. So, you know, you're definitely going to be computing your X bar. And you're kind of like wondering theoretically, how far off could the X bar be from the mu? And one way of thinking about that is like, how many standard deviations could the X bar be away from the mu? Now, the standard deviation of X bar is sigma over square root of n, but you don't know sigma. You could estimate, you could estimate the standard deviation of X bar maybe with S over the square root of n. And so this right here would be kind of an attempt to say how many standard deviations the sample mean is above or below the mean of the population that you're picking from. Well, anyway, define your random variable capital T like that, okay? It turns out that has the T distribution with n-1 degrees of freedom. And you can do some algebra to verify it. The book does it too. I take this fraction and I just divide on the top and on the bottom by sigma over square root of n. And then on the top, you are looking exactly at a standard normal. Now on the bottom, I need to like massage it a little bit more. I'm going to put an n-1 on the top, which means I need to also put an n-1 like on the bottom with this. And then I'm going to move the sigma from the top of the bottom to the bottom of the top. And I'm going to go ahead and cancel out the n squares because they cancel. And I'm going to express the whole thing as the square root of itself squared. And so the s that's there will square, and the sigma will square. And so I'll be left with the square root of all this stuff, the square root of n-1 capital S squared over sigma squared. And then on the bottom, there'll be an n-1. Now, the top, according to our previous big theorem, is chi squared with n-1 degrees of freedom. And here I am dividing by the degrees of freedom. So I've met the definition for a T random variable. Standard normal over independent chi-squared divided by its degrees of freedom. You see the independence is because the X bar and the S are independent. So that particular form of a T random variable is just super important in statistical theory all over the place. You ever go on and take a class in mathematical statistics, you'll see it a lot. So great triumph of probability theory to be able to figure out its distribution. That's all I've got for this section. So I will close down and see you soon.